Okay, continuing in Chapter 4, if you look at the top of your lecture note sheet, it had section 5.1. Scratch that out. I had a typo. This is actually section 4.2. So scratch that out and make it 4.2. We'll look at logarithmic functions, which in essence, where they come from is simple, but to work with them can be quite difficult and confusing. So pay close attention to all the objectives and the work that we're going to do here. You can read through all the objectives there. One thing we want to note on our calculator is this is calculator work. The common logarithms and the natural logarithms when we get to those. I'll explain to those as we get there. But here is where the logarithm function comes from. Remember the basic exponential function that we had over here? Let's say it was this type that increased. That had a horizontal asymptote there at the y-axis. Well, since this graph is a one-to-one function, passes the horizontal line test, it does have an inverse. The inverse of the exponential function is called the logarithm function. So that's where the logarithm function comes from. It's the inverse of the exponential function. And remember, the exponential function was y equal b to the x. Well, since it's one-to-one and it has an inverse, remember the property, it's symmetric about this line y equal x, a function and its inverse. So the inverse of this exponential would have to be a graph that looks like this. This is called the logarithm graph. Now, remember our RSSR steps on inverses. We swapped out the x's and the y's. So if I swap out those x's and y's, I end up with a logarithm equation to look like this. X equal b. Had to think about that for a minute. X equal b to the y. All I did was swap out or switch my x's and my y's. So x equal b to the y. This is an actual logarithm equation. This is the exponent we studied in the previous section. This is the one we're going to study in this section. The only problem with a logarithm in this format is that it's not in the actual function format. A function format has to be y equal to something. This one's not in the y equal to something format. So we have it defined here. So for a logarithm function, x has to be greater than 0, b has to be greater than 0, and b can't be 1. The logarithm function is going to take two distinct formats. You can look at a logarithm in this format that we can quickly see where it came from just from switching x's and y's, or the more appropriate format when it's in a y equals format looks like this. So in essence, a logarithm takes two forms. A logarithm comes in two forms. And each form will help us out with different aspects that we'll be working with. But both of these two I have circled green, both represent logarithm functions. It's a logarithm function with a base b. There's your base. Two forms, written right there. So important that you realize that. Our first thing is to convert from one form to another. From a log form to exponent form or exponent form to log form. So I pulled this study tip out of the book. To take when you have a logarithm in this format, to convert it to the other one, it's sort of like taking it full circle. It's going to be this base raised to that power equal to that variable. So we'll take it full circle. B raised to the y equal to x. B to the y equal x. And it's a conversion. We're just converting from this log form to that log form. And then we'll go the other way. if I'm given it in this format, I'm going to want to take it and write it over here in this format. Well, I've got to remember it's going to have a y equal log base b, so I'll know my b over here as my base is going to go as my base on my logarithm. And notice who gets the x and who gets the y. It'll be log base b. The x that stands alone goes here. The y that's an exponent goes there. So if I took this problem right here and brought it full circle, I'll have b to the y equal x. And that's what we have written. Bringing this full circle, 5 to the second power equal to x. 5 to the second power equal to x. Let's bring this one full circle. B to the third equal 64. B to the third equals 64. And even though this one's written backwards, we can still think of it as this y being on this side, y equal. And we can bring it full circle. 3 to the y equal 7. Just bringing it full circle. So when it's in a logarithm form, we can convert it to this exponential form. It's still a logarithm, it's just its different form. Now let's take them when they're in this format. Let's say 12 to the 12 equal to the x. When I come over here, it's going to be a logarithm. I have to know what the base is. And since the 12 is the base there, the 12 is going to be the base on my logarithm. Then I have to decide where the x goes. The exponent's going to stand alone. The x is going to go behind the log. Let's rearrange this guy. I know I'm going to have a log, and I'm going to have a log base 8. Not 8. Silly me. What's the base going to be? There's the base. It's going to be log base b. Now I have to decide where did the 3, where did the 8 go? Well, it's going to be log base b of 8, and that's equal to 3. Let's do one more. Log base, in this case, my base is 16, so my 16 is my base. And notice when you write the base on a logarithm, it's kind of dropped below the word log. So I have log base 16 of what? The exponent's going to stand alone, and the 4 is going to be with the 16. You'll get a lot of practice in the exercises on doing these conversions. But it's all, and this is really important, it all stems from being able to know this definition, how these guys convert. Let's look at some properties. Based on those conversion techniques, we could prove these, but let's look at some properties of basic logarithms. Log base any a of the number 1, always 0. Log base a of itself a is going to be equal to 1. Log base a of a to the x, the answer is x. And then a to the log a of x is equal to x. And what I call these guys are my, when the bases match, they cancel out properties. Notice there's a base a here and a base a there. If those two are matching, the answer is going to be what's in the exponent position, and since there's an understood exponent of 1, the answer drops out to be 1. This base matches with that base, so the answer is going to be the exponent. That base a matches with that base a on that logarithm. They cancel out, the answer is x. They cancel out kind of like that. The whole thing cancels. The log, the a, all of that cancels, and you're just left with, in this case, the exponent, in this case, the argument. So always think, if bases match, they cancel out. So some quick properties. Log base 2 of 1 equals 0, just illustrates that property. Log of 1 is always 0. Here I've stacked the bases. Log base 5 of 5, they're stacked. The exponent's 1, so the answer's 1. Log base 7 of 7 to the third. The bases are stacked, so the answer is 3. 8 raised to the log 8 of 3. The bases are stacked. 8 log 8, that cancels out, and the answer is just 3. So we're looking for the bases to match. So let's consider these 6 and just look automatically and see, well, are there any where my bases match automatically and I can cancel them out and get my answer? You might say, yeah, log base 8 of 8. That's all matching, so the answer is just 17. See another one. 3 log 3 of 5. Bases match, they cancel, the answer is 5. Here's another one. Log base 7 of 7. Bases match, the answer in this case is 1, the understood 1. So those are 3 real easy ones where the bases match. Some of them you have to force the bases to match, although, do you notice just kind of a sore thumb one sticking out that follows this property up here? Those should always be a quickie. Where is it? Log base 6 of 1. Don't even think about it. Log of 1 is always 0. Now we're going to have to play around with the 2 that are left. When the bases don't match, what you have to do is configure it where you can basically force them to match. Log base 9 of 81, 9 and 81 don't match. But is there a relationship between 9 and 81 where I could write this where my bases are stacked? So 81 is the same thing as 9 to what power? 9 to the second power. If I can write it to make my bases match, then that stuff is going to cancel and I'm just left with the exponent of 2. So it's a game. Play the game, make the bases match. Let's play the game over here. I've got a log, base 6, and I have a square root of 6. Well, the only way I can cancel bases is if it's a plain 6, a plain 6, and a plain exponent, or an exponent. How can I write the square root of something as that to a power? This is important. You need to remember this from a previous algebra class. The square root of 6 is the same thing as 6 to the 1/2. Square roots are equivalent to 1/2 exponents. If it were a cube root, it would be a 1/3 exponent. Fourth root, 1/4 exponent. Know that roots convert to exponents, which will allow us to make our bases match. Cancel them out, and the answer is 1/2. These will take some practice, but there's plenty in the exercises for you to practice on getting used to making those bases match. None of these logs that we just did here could we do on a calculator. These guys here can't do on a calculator. Our calculator is reserved for those problems that are only 2 specific bases. Our calculator will only do log base 10 or log base e. The way they look on your calculator, log base 10 looks like this, LOG. We don't put the base 10, it's understood to be base 10. On your calculator, log base e won't be written that way. It's going to be written as LN on your calculator. So LOG, if there's an x, is an understood base 10, called the common logarithm. LN, if there's an x, LNX, is known as the natural logarithm. And those are the only ones your calculator will do. So practice on your calculator. Let's find some values. LOG of 134. So let's hit the LOG button here. 134. Close that parenthesis and enter. So 2.127. Let's do ln, find the ln button, and let's type in 85. I lost that number, 4.44. Let's hit the next one. Log of 3 times the square root of 2. 3 square roots of 2. 0.627. Let's do next one. ln negative 7.39. Is that right? Yeah. Doesn't matter because you should get an error. See if you get an error on ln of negative 7.39. I'll explain why. And let's do the last one, log of 1,000. So log button, 1, 1, 2, 3. Should be 3. I didn't want to do that. Okay. Here is why ln of negative 7.39 has an error. When we came back here and I was talking about the logarithms, I didn't mention the domain, but look at the graph of this logarithm. This logarithm is going to have a vertical asymptote here at 0, and this graph is going to approach that asymptote and lie strictly on the right-hand side of that x-axis. Your logarithm graph will only have a domain of numbers greater than 0. You can't take the log of a negative number based on this domain restriction. That's why when we went to calculate this, there's an error. You can't log a negative number. It's not in the domain. So up here, if you ever want to calculate a log, if it's not log or ln, you can't do it on your calculator. We have to do it by way of the properties. Now the same properties I mentioned above work with both ln's and tens, log-based tens. So I've rewritten them in terms of the ln's. ln1 is equal 0, ln e is equal 1, ln e to the x is equal to x, and e to the ln x is equal to x. These are the same properties as before, but you won't recognize them, so I suggest you do this. The ln has an understood base of e. I suggest you pencil in that base of e every time you see an ln until you get used to it. Every ln has a base of e. Well, we know from previous, ln1 is always 0, or log of 1 is always 0. Look at this. When you write in the e, you see the bases are stacked. And e, they match up. The answer is 1. They cancel out. There's an e, they match up. The answer is the exponent. There's an e, they match up. The answer is the exponent. So it's still the same bases match deal. Suggestion though is to write in the e so you don't get confused, and so you'll see that they do match. So I'm going to practice that here. I'm going to go ahead and write in my e. So ln base e of e to the 8 has to be an 8. Here, if I see a log without a base, I'm going to pencil in a 10. That tells me they match. The answer is 53. If I see an ln with no base, I'm going to go ahead and put in the understood e. They match. Answer is 45. This one, I'm going to have to play around with that. Let's rewrite it. I know that's an ln of e, ln base e. but I have to write 1 over e to the 5th in a way so my bases would match. So I have an ln of e, and I want to write this as e to some power. If I can do that, then my bases match and they cancel out. 1 over e to the 5th is the same thing as e to the, anybody got an idea? E to the 5th, but if I make it negative, that gives me the reciprocal of 1 over e to the 5th. So think of reciprocals. Reciprocals involve negative exponents, so 1 over e to the 5th is equivalent to e to the negative 5. With all that rearranging, I see my bases are matching, they cancel out, answer negative 5. Tricky. Finally, this last guy. Since it's an log, I'm going to go ahead and write in the 10. And now I have to play the game of how can I rewrite the number 1,000 as 10 to some power? Well, it's 10 to the 3rd. And by rewriting it, I can wipe those out and get an answer of 3. So you got to play the game, whether it's a ln, a log, or any of the other logs that we mentioned. Bases match, they're going to cancel out.